All right, welcome again to Advanced Modeling Methods. And so at the end of last class, we basically concluded on how to set up the system of equations for calculating the boundary values that are not known. Remember that half of the boundary values are known, either temperatures or Qs, or a combination of the two, or either all temperatures or all Qs. And then what we basically do with the boundary element method is just create an algebraic analog to relate all the temperatures and all the fluxes on the boundary with each other, and then move what we know to the right, keep what we don't know on the left, and then solve for what we don't know. So set up a square system of equations, simultaneous system of equations, ax equal b, and that x contains the information that we don't know. So it is as simple as that, but obviously to get to that point, there's a lot of things that need to happen. All these elements of these matrices are kernels that are integrated from fundamental solutions and so on and so forth. And today we're going to put that into practice, okay? So we're going to, before we get to that, we're going to talk about how to post-process. So remember the boundary element system of equations, or the discretized BIE, the discretized boundary integral equation, allows you to find the unknown boundary information. But how about the interior information that you want? You might want to know what the temperature is somewhere in the interior, or everywhere in the interior. So we'll look at how to do that, and then we'll go back and implement it on a MathCAD code, very simple MathCAD code. Later next week we'll add some things to that, and then actually come up with our own high-level program to perform these operations. All right, so advanced modeling methods, and this is lecture number 12. All right, so we're going to talk about post-processing. And that's short for, well, finding wanted interior or internal information. That would be, well, what if you want to know the temperature? What if you want to know the TDX? What if you want to know the TDY? For instance, how do you go about that? All right, so recall that the system H times T equals G times Q is on the boundary. So these are all the temperatures on the boundary, these are all the heat fluxes on the boundary, was reorganized as A x equals b, where x contains the unknown boundary information. That is T's or Q's. The T's or Q's that we don't know on the boundary then are found on X. So basically, after solving AX equals B by means of, well, you can do a direct solution method, you can do Gaussian elimination, you can invert the matrix A, you can do whatever, you can apply whatever method or whatever library you have out there to solve a system of equations. It's pretty standard. After that, all the boundary information is known. That is Tj Qj at j equals 1 through n. So now we know all the temperatures and all the fluxes on the boundary.
Professor?
Yes, sir.
New original equation, you have the temperature times H represent what in the system?
Huh?
Just your representation. You have G times your heat flux, and H times, what is H?
H?
Yeah.
Well, we've been talking about it for 2 weeks.
Yeah. I didn't know
Okay, H is a matrix, it's a fully populated matrix that contains every one of these elements is an integral. It's an integral of the normal derivative of the Green's function. So G, it's better explained.
Yeah.
G is a fully populated matrix that contains the integral of the fundamental solution, the Green's function, G, which is the log of the square root of x minus plus y, so on and so forth. The integral of that function over every one of the elements, collocated at every one of the elements. So it basically gives you the interaction of all the Q's, how each of the Q's influence every one of all the other Q's, and how each of the T's influence all the other ones, all the rest of the T's. As a function of the discretization that you established, right? Because you have a boundary, you decided a priori that you wanted to break up that boundary into so many elements, so many boundary elements, okay? N in this case. Now, so we find the H, you find the G, which is the purpose of any numerical method, right? The purpose of any numerical method is to take a complicated set of differential equations and boundary conditions and turn it into an algebraic analog, okay? Break it up, discretize it, and turn it into an analog that you can solve as a system of equations, okay? Now, the solution of the system of equations, X represents the information of the boundary that you don't know. Because some of these T's you know, some of these Q's you know from boundary condition information, right? For the problem to be well posed, some of the T's or some of the Q's or all of the T's and none of the Q's must be known, okay? So at least every element that you discretize, you have to know either the T or the Q on every element. And what you don't know comes out of these after the rearrangement or the rearranging of the system. All right. So basically, after solving the system, now we know what we knew a priori, which was the boundary conditions, plus whatever we found, which is the stuff that we didn't know. So now we know everything on the boundary. So how we go about solving for things in the interior? So now post-processing. All right. So, how to compute T at any internal point xi I, which is xi yi. All right. So what do? We go back to the discretized boundary integral equation. Now the collocated one, just the discretized version. So we have T xi, T times C, plus the summation from j equal 1 to n of Tj times the integral over delta gamma j of H is equal to the summation from j equal 1 to n. And we're calling this one psi I to denote that that would be an interior collocation point. Qj times the integral over delta gamma j of g x psi I d gamma. All right, and that's where that matrix H and that matrix G come from. By locating the psi on the interior, you generate an n by n system of h's and an n by n system of g's. But now psi is any point in the interior, knowing that we already know this and we already know this. So this is known and this is known. So this is pretty straightforward because all we need to do is recall if xi I belongs to omega, is an interior point, then c psi I is equal to 1. And therefore, t at any interior point will be equal to the summation from j equal 1 to n of qj times the integral minus, I'm going to put in bracket here, tj times the integral of h x psi I. All right, so that's it. All we need to do is reevaluate this summation of integrals, multiply times the boundary values, which are all known now, t's and q's, and now we have the temperature. So basically the temperature at any point in the interior of a domain is a weighted average between fluxes and temperatures in the domain and their corresponding weights. So these take on the place of weights. So it's just a weighted average of all these. Now we don't have to worry about singularities, because remember, we're placing the point somewhere in the interior of a domain, right? And we're integrating only around the boundary. So the integration point will never coincide with the interior point, because we're only integrating along the boundary and the interior point is in the interior. So these will never be singular. So we don't have to worry about singular integration or anything like that. We just perform numerical integration of those values, and that's it. All right, so that's how you calculate the temperature. How about if you want to calculate the fluxes in the interior? Now the flux in the interior is not a scalar. The flux in the interior is a vector that has two components, the flux in x and the flux in y. We call the flux on the boundary a scalar because there's a normal vector associated with the boundary point. So when we multiply qx times nx and qy times ny, we get what we call a normal flux. Okay, this is the total amount of energy leaving through the boundary. Okay, now in the case of the interior, you cannot calculate a normal flux because there is no normal vector at any interior point. So you need to discern or discriminate between the dx and the dy. So if we want to calculate the x derivative of these, we have to do it independently from calculating the y derivative of these. All right? Now, we go to all right. So how about dt dx and dt dy and remember this x denotes x and y, and the xi denotes xi yi. Okay, I'm just not using the entire dependency of those functions. This function depends on x, y, xi, and yi. All right, so now rewrite expression above with full dependency. So basically this will be the temperature at any point xi, yi in the interior is equal to the summation from j equal 1 to n of qj times the integral over delta gamma j of g x y x I y I d gamma minus tj times the integral over delta gamma j of h x y x I y I d gamma. So if we want to calculate the x derivative of t, we would have to differentiate with respect to xi, not with respect to x, because x is an integration point. Xi corresponds to the field point now, where we want to calculate the flux, and we just calculated the temperature. So this will be the summation from j equal 1 to n of qj, and then this will be the integral over delta gamma j of dg dxi xy xi yi. So now we have to differentiate with respect to xi minus tj delta gamma j dh dxi xy xi yi d gamma. And similarly, dt dy I at xi yi is equal to the summation from j equal 1 to n dg dy I xy xi yi minus tj dh dy I So that's how you calculate the x and y gradients internally. But again, it would require n integrations. Well, n times 2 integrations. It would require this integration n times, and this integration n times. And we need to find what these functions look like. Right? We know what g looks like, we know what h looks like, but what do they look like now when differentiated with respect to xi and differentiated with respect to yi? So, for instance, recall g of x, y, xi, yi is equal to minus 1 over 2 pi times the log of x minus xi squared plus y minus yi squared. This was called the Green's function or fundamental solution to the Laplace equation. This is free space fundamental solution. Alright? So dg dxi of x, y, xi, yi, if we differentiate that with respect to xi, what do we get? Well, it would be the derivative of the log, which is 1 over the argument, 1 over the square root of all that, times the derivative of the argument, which is all that stuff. Or I can take that 1/2 and put it over here, multiply that 1/2 times this 1/2, that'll make it easier. But the internal derivative of x minus xi will be minus 1, because xi is negative. So now these will disappear, the negative sign will disappear, it will be 1 over 2 pi x minus xi divided by x minus xi squared plus y minus yi squared. And it's positive, as you can see. And dg dyi is also positive, y minus yi, x minus xi squared plus y minus yi squared. Also, h of x, y, xi, yi was equal to minus 1 over 2 pi x minus xi times nx plus y minus yi times ny divided by x minus xi squared plus y minus yi squared. We already knew that. We already derived that one long ago. And now we need that one with respect to xi and that one with respect to yi. So, for instance, this h with respect to xi will be equal to, it's positive, 1 over 2 pi, and then we'll have y minus yi squared minus x minus xi squared times nx minus 2 y minus yi x minus xi times ny. All of these divided by x minus xi squared plus y minus yi squared squared. All right, and you'll see it looks complicated, looks like very rigorous, but you'll see how easy we can implement that on a code. Easier than doing separation of variables and superposition and all that to find an analytical solution.
Professor, is that gamma x or sorry, not gamma, eta x or eta y or h, or is that just n?
And where?
On the h x and y of x of x. Is that nx?
This is x. This is y.
Right above it.
NX.
It's nx. Right. So
Yeah, and x and y. Those are the components of the normal vector. And finally, the h dyi is equal to 1 over 2 pi. And this one will be, this one would be x minus xi squared minus y minus yi squared times ny minus 2 x minus xi y minus yi times nx x minus xi squared plus y minus yi squared, all of this squared. All right, so these are the two derivatives of g, and these are the two derivatives of h. And now we have everything we need to perform post-processing. So with the first system of equations, we find the t's and the q's that we need on the boundary. After that, we have all the information we need on the boundary, t's and q's. Problem is solved. Then we use that information in a post-processing stage to find temperature and gradients anywhere on the boundary, anywhere we want on the boundary. All right. So let's formulate a simple problem that's actually not so simple, but you'll see how we can implement all of these on a 2-page MathCAD code and compare to the exact solution. So I'm going to formulate a problem that has an exact solution so that we can compare apples to apples. Let's see how close we can get to it. All right. So, all right, so let's formulate this problem where we have the Laplace of T of X and Y is equal to 0. Okay, so steady heat conduction with constant conductivity in a rectangle. This is size L and this is size small l. Let's say that it's insulated on the left and on the bottom. So here Q is equal to 0 and here Q is equal to 0. Okay, so the derivative, the normal derivative here is 0, the normal derivative here is 0. So there's no energy crossing those boundaries, fully insulated. And that will be the case for all the elements that you decide to place along this boundary and all the elements that you decide to place along this boundary. On the top, let's say that temperature is equal to 0. And then on the right, we need a non-homogeneous boundary condition, because if we say something is equal to 0 here, the solution is 0, right? We need something different than 0. But I'm not going to pick a number. And the reason I'm not going to pick a number, I could pick Q equal 1, for example. That would probably give me a nice looking solution. But if I pick T equal to 1 or T equal to 100, what's going to happen is that you're going to have a discontinuity here at the corner, right? So if you pick T equal to 100 on this wall, that's okay. You can solve that problem analytically. That analytical solution is going to be in terms of infinite series, Fourier series. But those series are going to have a hard time converging because of that jump here on the corner, that discontinuity. The BM is not going to have any problem. The BM is going to solve it just fine. So what I'm going to do is I'm going to pick a temperature here, a temperature profile that goes to 0 at the corner, right? So that we can get a solution in terms of infinite series that doesn't go crazy, so that we can compare exact solutions or semi-exact solutions to BM solutions. So we're going to pick a TL as a function of y. All right? So, such that if this is the y-axis and this is temperature, let's do like a parabola, right? Where this is just the maximum value TL. So TL of y, let's say, is equal to TL times 4y over L times 1 minus y over L. That's quadratic, maximum at the center, and 0 at y equals 0 and at y equals L, right?
TL, right, what's right in front of the y over L, the first one?
4. All right, is that clear? When y is equal to 0, this is 0. When y is equal to L, this is 0. When y is equal to half of L, we get 1/2 times 1/2 is 1/4. That 1/4 and this 4 go away, and we get that value TL, which we pick whatever we want, 100 or whatever, right? And this will avoid having that corner problem, which is not a problem for the BM. The BM will handle that, but those infinite Fourier series have a hard time converging when you have these type of jumps. All right, so using separation of variables, and orthogonality of eigenfunctions, we find that T of x and y is equal to the summation from n equals 0 to infinity of Cn times, this will be the cosine hyperbolic, yes, of lambda n x times the cosine of lambda n y. See? Yeah. Such that lambda n, the eigenvalues, is equal to, let me see, that would be the pi halves repeated, yeah. So it would be pi times 2n plus 1 divided by 2l. So the eigenvalues. And Cn this one. And Cn is equal to, oh, using orthogonality, if you remember these from math, you'll get, you need to integrate the boundary condition with the eigenfunction. The eigenfunction is the cosine TL divided by lambda n times L squared times the cosine hyperbolic of lambda n times big L times 2 minus 1 to the power of n divided by lambda n times L minus 1. Alright, and that, if you evaluate that series at any point in x and y, you should get the solution to that problem. This is the exact solution, and again I say exact, it's analytical, but it's not exact unless you manage to evaluate all infinite terms of the series, which is impossible. So even exact solutions are not really exact. But at least it's something analytical, at least it's a point of comparison. Okay? Now, the reason I picked the solution again, we will have a non-symmetric solution. It will be non-symmetric. Okay, you don't have a line of symmetry anywhere because there's no mirror. Even though you have flux equals 0 on the left and on the bottom, the boundary condition on the right and on the top are different from each other. So the contour plot of these will look completely slanted. There will be no line of symmetry, and that's what we wanted to compare. We want to compare the robustness of how the numerical method is able to capture these, even at very low discretizations. Okay, very few points. All right. Here. And all right, we're ready? So let me go back to the computer. Okay. So here's what I've done. Let me blow this up a little bit more. Maybe easier to see. All right. So we have an analytical solution, and let's pick. I'm gonna pick the maximum temperature on the parabolic profile on the right to be 100. I'm gonna pick this to be a square from 1 and 1. Okay, perfect. 1, 1 square. The eigenvalues, pi 2 times n plus 1 divided by 2 over L. Okay, we already talked about what the origin means. Okay, and we're gonna set up some arrays, so I want the origin to start at 1. And inf is just a variable that I'm calling infinity. Okay, because obviously I'm not going to evaluate infinite number of terms in a series, so I'm just gonna evaluate, I'm gonna say 50 is enough for these to decay. Notice that this decays with lambda n squared, actually lambda n cubed. So if those eigenvalues make the coefficient decay very fast as the element in the series increases. So here's the series solution. That's a constant of integration found by orthogonality. This is the eigenfunction, this is the eigenvalue. And then I'm going to also differentiate this with respect to x and differentiate it with respect to y because I want to compare the fluxes. I want to compare the gradients to the analytical gradients. So the derivative of these with respect to x is very simple. It's the sine hyperbolic times lambda n. The derivative of that with respect to y is very simple. It's the sine hyperbolic, the sine times lambda n. All right? So nothing out of the ordinary here. Just basically program that analytical solution. And now I want to plot it. I want to see how it looks like. And I'm going to plot it over 41 points. That's not the discretization I'm going to use for boundary elements, just to display, okay? I'm going to plot this over 41 points in the x direction and 41 points in the y direction. I can pick whatever numbers I want. I just want to have a nice looking display of the contours of the heat map, all right? So I'm going to create an index I that goes from 1 to ni, an index j that goes from 1 to nj, and what I'm going to do is create a 2D array called T exact. That's indexed by I and j. Alright? And it's indexed by I and j, where is basically the elements of this matrix T exact are the evaluation of this temperature over here at values of x and values of y that depend on the index I and j. Alright? And look how am I using the indices to generate values of x's and values of y. So basically a uniform point distribution in the x direction that depends on I, and a uniform point distribution in the y direction that depends on j. Okay? So in the x direction we go from 0 to L and 41 steps, and in the y direction we go from 0 to small l and 41 spacings. So I'm basically just filling out a matrix. And the reason I want to fill out a matrix, that's a matrix, it has 41 rows and 41 columns. The reason I want to fill out a matrix, by the way, if I make this 11, then I have 11 by 11, oops. Then I have an 11 by 11 matrix. So then when I plot that, it's going to look a little there's going to be kinks because the discretization is two cores. All right. I can also do a surface plot. I can do a wireframe, whatever I want. But the reason I made up a matrix is because the only way you can do 2D plots or 3D plots in this case in MathCAD is by plotting up a matrix of values. Same thing that you have to do in Excel. All right. So let me delete this. Let me increase the discretization here. Put in the original 41. And nothing changes because we're evaluating the same T, the same analytical solution. I'm just evaluating at more points. So it looks a lot smoother. So that's how the exact solution should look like. Those 50 terms on the series should be enough for that series to converge. And that's the reason I picked this solution. It has this weird behavior here. It's completely unsymmetric. And I can plot it in 3D too. Actually, I'm going to copy this whole thing here, and double click, and I am going to make this a surface plot, and that's how the surface plot looks. But I'm going to look at the appearance, full surface, and do a color map, and there you go. Right, and I can just rotate it to make it. What I want. Notice that the parabolic behavior on the right wall is perfect, as I intended. Alright, come on. You can use the scroll button to zoom in and out and so on. Alright, good enough. Alright, so now I'm gonna do a BEM solution. Alright, and in order to do a BEM solution, the first thing I need to do is discretize the geometry. I know that my geometry now goes from 0 to 1 and the x direction, from 0 to 1 in the y direction. So this BEM code that I've set up can solve any heat conduction problem in a rectangle L to L. Any heat conduction problem with any types of boundary conditions. Okay, you just set up the boundary conditions and it'll solve it for you. So the first thing I'm going to do is I'm going to say, well, I want to discretize the x direction with 3 elements. That will be the same for the bottom and the top plate. okay? And I want to discretize the y direction with 3 elements. So I'm going to use this very coarse discretization, a total of how many? 12. 12 elements, okay? 3, 3, 3, and 3, okay? If you try 12 elements with any other method, you won't even get a solution, okay? But I'm going to show you that even at this very coarse discretization, we can actually get a solution with BM, all right? So what I'm going to do, basically, is everything that we've done on paper. Let's say before we do something here. Everything that we've done on paper. First, I'm discretizing. Notice that I'm discretizing counterclockwise. We always follow a counterclockwise direction to guarantee that the normal vector always points out. All right? So I'm going to go from 1 to nx. I'm going to start from the bottom, and I'm going to say, I'm going to define point 1 and point 2 of the first element. Remember, every element has 2 points, starting and final point, because we're using linear elements. Later, we're going to use quadratic elements, so you're going to have 3 points per element. Okay? So point number 1 is going to be j minus 1 over nx times L, and point number 2 is going to be j over nx times L. All right? So depending on the number nx you pick, you're going to have more or less points. And the coordinate y is going to be 0. We're talking about the bottom plane. All right? Is that clear? All right, and I'm accumulating n, okay? N is going to be the total number of elements, okay? Which is, at the end is going to be 12, obviously. But I'm accumulating, I'm starting at 0. Then I'm going to say n is equal to nx. So far, I've laid down nx elements. And I'm going to go lay down another ny elements. I'm going to go to the right wall. There's no reason why to follow a specific sequence as long as you do it counterclockwise. I can do this one, I can do that one, then I can do this one, and then I can do that one if I wanted to. Okay? But just for order, I'm going to go the whole round. So I'm going to go from 1 to ny. So I'm going to do ny elements on the right hand side. The coordinate of the x direction is L. See? And the coordinates of the y direction are j minus 1 over ny, j over ny, times small l. So I'm discretizing in the y direction. Then I'm going to go to the top plate. Now n has accumulated nx and ny elements, nx on the bottom and y on the right. And again, I'm going to go from 1 to nx because I want nx number of points on the right. So the coordinates of y on the top plate are small l, okay? And the coordinates of x1 and x2 are, well, first point, second point, first point, second point, first point, second point, so on and so forth. All right? You're going to see graphically now that this makes sense. And then finally, the left wall, and I've accumulated so far 2nx and an ny number of points. And I'm going to go on the left wall, the coordinates of the x coordinate. The x coordinate on the left wall is 0, the y coordinate goes from top to bottom, first point, second point, and so on and so forth. So with 3 points, let me skip the next couple lines, and I'll explain you what that is. Okay, this is what it looks like. This is what that discretization looks like. All right, I picked 3 points, or 3 elements per side. That's the bare minimum I can do. Okay, BM will work if you pick 1 element aside. But remember, we have a boundary condition that changes as a function of position. So the information, you have to give it more than 1 point, otherwise the BM is not going to know what to do, right? It's not going to find any unsymmetries or anything like that. So at least 3 points so that, well, the temperature is going to be 100, here's going to be whatever, 25, and here's going to be 25, okay, from that parabolic boundary condition. That's given information. If I change the number nx and ny, let's say I make it 11 and 11. And the reason I'm picking an odd number is because I want a point in the center, right? Just to pick the maximum of the parabolic profile. Right? So that's 11 points on each side. At the end, there's 44 elements. Okay, the red crosses are the starting and end points of each element, and the blue dots are the collocation point at the center of each element. Okay? So let me go back to, let me go back to 3. All right, I'll change those later to compare answers. Okay, what else? Now, I can say that the number of elements is 2n x's and 2n y's. So I'm going to go all the way from 1 to n. And I'm going to calculate the length of each element. Remember, I need the length of each element because that's the Jacobian for the integration. Okay, that's going to go on the integration. And I'm going to calculate the midpoint of every element, xm, ym. Right? That's a collocation point, the center of each element. And I'm going to calculate the normal vectors of each of the elements. Remember the normal vectors for linear elements, y2 minus y1 over the length, and the y normal vector will be x1 minus x2, is flipped, right? So on the right wall, for example, the normal vector points to the right. It's 1 in the x direction, 0 in the y direction. So this should be y2 minus y1, y2 minus y1 and x1 minus x2 gives you 0 on the right wall, and so on and so forth. On the bottom wall, when x is going up, the normal vector is negative y, negative 1, and the y direction. All right. Now I need to tell the code what are the boundary conditions, right? So I need to go again wall by wall because each wall has a completely different boundary condition. And I'm using a code here called KB, right? So I'm going to go from 1 to an x, 1 to an y on the right, 1 to an x on the top, 1 to an y on the left, right? Bottom, right, top, and left. And KB indicates the type of boundary condition, right? Where 1 means temperature, 2 means flux, right? And the original problem that I gave you, the bottom, we specify the heat flux. It was 0. And on the left, we specify the heat flux, and it was 0. So we specify the heat flux, and the value of it is 0. On the bottom, heat flux, value 0. On the right, we specify the temperature, and the value is given by this parabolic profile, right? So that's a given information, and the given information comes from this parabola, evaluated at the midpoint of every element. TL times 4, ym over L, 1 minus ym over L. It's a little confusing because this is an L and this is a 1, although they look almost identical. I think it's a pixel that.
The L is just like 1 pixel
Yeah,
taller.
the bottom. The bottom has 1 pixel on the right, 1 pixel on the left. But obviously that's impossible to see if you don't see them side by side. Anyways, all right. On the top, I told you the temperature was 0, so the type of boundary condition is 1 for all the elements on the top, and the boundary condition is 0. So you can change this to whatever you want. You can change this to whatever you want, would you just be solving another problem, right? You can change the boundary condition types and the boundary condition values to whatever you want, and you'll just be solving another problem. We'll see in a minute. All right. So now I have information about geometry, the discretized geometry. I have information about boundary conditions. Which ones I know, temperature or flux. So the next step is, well, I'm plotting what the discretization looks like. The next step is to calculate the influence coefficients. The influence coefficients is just by performing collocation, I calculate the matrix G and the matrix H, okay? Remember, the Green's function is minus 1 over 2 pi log of that. And H is the normal derivative of these, which is this one times nx and this one times ny. Right? Same thing that we've been writing over and over. So, and remember the parameterization of the geometry as a function of eta on every element. X is parameterized as a function of eta as x1 times the first shape function plus x2 times the second shape function. Okay, I haven't written anything here that we didn't write on the notes. So let's see how we do collocation. Here it is, simple as that. Collocation, you collocate I on all the boundary elements and integrate over all of the boundary elements. This is collocating the source point of the direct of the function in the center of each boundary element and integrating over all n boundary elements. Okay, so the elements ij of the matrix G, of the influence coefficient matrix G, are the integrals of the Green's function. The Green function x parameterized with these, y parameterized with that, and instead of d gamma, now we have d eta times the Jacobian, which happens to be the length over 2. Okay? we transform an integral over a line integral into an integral of the eta from -1 to 1 and found the Jacobian to be the length of the element divided by 2. And that's it. That's G. Now, it is easy here on MathCAD because MathCAD can perform the numerical integration for you. You can actually right-click here and you can decide what type of integration you do. You can do singular endpoint, infinite limit, adaptive, that's the one I picked, or Romberg integration. You can do trapezoidal. Well, Romberg is kind of a high-order trapezoid. Okay, Hij now is just basically the integral of h. This is h, the integrand. This is h and x, hy and y. And that's it, from -1 to 1. Now remember that the diagonal elements of G are singular, right? Because we're integrating, and at some point the log is going to become the log of 0, and then there's going to be a problem here. So, but we derived what the diagonal elements for linear elements would look like. And it would just simply be that much. Okay? The length of the element divided by 2 pi times 1 minus the log of the length of the element divided by 2. If we want to compare what the adaptive integration did, for example, let's say I want to compare the element G, let's say 3, 3, which is a singular element, right? Which is a singular element on the matrix. It's an integration over element number 3, which is the element down here, when I put the source point of the directed function right in the middle of it. I got 0.148 through adaptive integration. And the exact value of G33, I'm replacing it here, would be 0.148. So the adaptive integration didn't do a bad job, as you can see. It actually, if I even if I increase the resolution of these, let's say I want to do, let's give me 8 decimal places, and this one give me 8 decimal places. Let's see how good did it do? Wow, perfect. Okay, remember that this one I'm evaluating right after I do this, which is already replaced by the exact solution. So the adaptive integration does a really good job even at capturing a singular integral. All right, so let's forget about this. Let's forget about this. So I'm replacing the diagonals of G by that. And also remember the equipotential technique, that I can replace the diagonals of H by the sum of the off diagonals. Right? I can replace the diagonals of H by the sum of the off diagonals. I can make the diagonal 0, then add up all the diagonals on that row, all the elements on that row, and say now that the diagonal element is equal to minus D. That's the sum of the off diagonal. And at the end of the day, it should be, that should be the right answer. All right, so I have a matrix H and a matrix G. How big are these matrices? I'm going to print them, I'm going to display them right here. How big are these matrices? Remember? 12 by 12, okay, 3, 3, 3, and 3. So we have, and they're fully populated, and they're not diagonally dominant. They're not diagonally dominant. Even though the diagonal looks to be bigger than the other ones, it's not much bigger. That's not a diagonally dominant matrix, and therefore it's not a matrix that you can decompose very easily. You need to be careful, but MathCAD will do that for us. MathCAD will actually do the decomposition and solution of the system for us. And H looks sparse. It looks sparse because we have flat segments. Okay, and the normal vector is always perpendicular to the direction of integration. So when we put the collocation point on the first element, the integral of H over the first 3 elements is equal to 0 because the normal points down and the direction of integration points to the right. All right, but it's normally not sparse. Normally there's not a lot of zeros. Okay. Oh, by the way, well, we can figure that out later. All right, so I have H, I have G. What do I need to do now? I have H times T and G times Q. But some of the T's I don't know, some of the Q's I don't know. Exactly half of the T's I don't know, and half of the Q's I don't know. I know Q here and here, on these 3 elements and these 3 elements, and I know T there and there. So what I need to do is flip some columns of G and some columns of H, right? Move them around to form that system AX equal B. And then solve for X, and X will contain information about temperature or fluxes that I don't know. And I do this in a very simple flow loop here. Okay, I'm going to make the matrix A 0 and the matrix B 0 to start. And I'm going to say, well, look for all the elements from 1 to n. Now, if the boundary condition of that element is equal to 1, what does that mean? I know the temperature. KB is a type of boundary element. If it is equal to 1, that means that I know the temperature. If I know the temperature, make the jth column of matrix A the jth column of matrix G negative. So I'm flipping J, putting the negative first column of G into A and the negative of H into B of that column. I'm accessing the entire column, the jth column of A, making it the jth column of G. If the boundary condition is type 2, what does that mean? Flux. Then A, the jth column of A will be filled with the jth column of H, okay? And the jth column of B will be filled with the jth column of G. Okay, nothing out of the ordinary there. I could have done that with a double loop, but I just decided to just access the entire column. Replace the entire jth column of A with the jth column of G. All right. The right-hand side vector, now the B, A contains elements of G and H, and B contains elements of H and G. B is on the right-hand side, multiplying everything we know, and A is on the left-hand side, multiplying everything that we don't know. So B now multiplies the vector of boundary conditions. This vector of boundary condition contains fluxes, temperatures and fluxes, but it is arranged already in a way that when I multiply times matrix B, I get a right-hand side vector B. And now all I need to do to solve for X is do a linear solution of the matrix A and vector B. I can also do A to the minus 1 times B, okay, but this is a little bit more accurate. Always calculating the inverse is a very computationally intensive, high round of error type of solution. All right, now I have X, and X contains the boundary information that I didn't know before. So I'm going to do another loop and basically say, fill out the solution vector T and Q. If the boundary condition type is equal to 1 for element J, then that means that I knew the temperature. So the temperature vector is going to be filled with the BC, boundary condition vector, while Q is going to be filled with X, with element J of X. And if the boundary condition type is equal to 2, well, I'll do the opposite. That means that I originally knew the flux, so I take the flux from the BC, and I take the temperature from the vector X. Is that clear? All right. So I return T and Q inside an array of 2 elements, and that will actually take on the values of 2 arrays, TBM and QBM. So QBM and TBM are arrays of 12 elements. Just 12 elements for T, 12 elements for Q. All I'm doing is boundary solutions. So if I do T, oops, I need to do this after these. T. Oh, sorry. It's called TBM. It's only 12 values of temperature. And those are arranged in the sequence in which I arrange the elements. 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3. All right, and same thing for the flux. Notice, if I print the flux, well, obviously the first 3 are 0 because that was given, that was a boundary condition. Then those are the fluxes on the right wall, those are the fluxes on the top wall, and the fluxes on the left wall are also 0 because those were given. All right. So now I'm going to display and two plots with the exact solutions and the BM solutions to compare for accuracy, at least qualitative accuracy, even using 3 points, 3 boundary elements on each segment, which is very, very low discretization. You cannot even get an answer if you do this. If you do 12 degrees of freedom and boundary and finite elements or finite differencing or finite volumes, you will not get an answer. It is not perfect, but it's somewhere in the neighborhood, okay? It is a little different on the first 3 points. See, the blue line is a boundary element solution, the red line is the exact solution. On the first 3 points, it differs a little bit, but even on the left-hand side, which are the last 3 points, 1, 2, 3, I should have done, let me do that real quick. Second trace, I can do like, I can do this, and no line. Right? So let me see the flux. The flux, which is usually a lot more difficult to match. If you do finite differencing, the flux will be all over the place, even, or especially because you have a very coarse discretization. Let me do symbol here, and I'm going to do this, and no line. So it's a little bit more visual now because the BM is a discrete solution, while the red one is supposed to be a continuous solution. Well, it is on the neighborhood. It is giving me the information. Now, if I increase the resolution, can I expect this solution to be better? Well, let's see. I'm going to go from 3 points on each side, on each segment to, let's say, okay. Let me put 11 points on the x direction and 11 points on the y direction. The discretization looks like this. That's the temperature, almost on the nose. Boundary temperatures. And look at the fluxes. Okay? Well, the flux is a little off right at the 2 corners, corner here and corner there, because there is an actual discontinuity of fluxes at those locations. Okay? The discontinuity of fluxes come from the fact that you have a temperature profile in the y direction. A temperature profile in the y direction, so therefore the derivative with respect to y is not 0. The derivative with respect to y of a parabola is not 0. And I am telling you the flux on the bottom wall is 0. So there's a discontinuity of fluxes and it's trying to handle that. However, I don't know whether the analytical solution is completely correct. Those series are well behaved. But let's see, if I make, I'm going to go, okay, I'm going to go all the way to 41 points. 41 points, which is not an end of the world discretization. I'm talking only about 164 elements, okay? In a 2D problem, 164 degrees of freedom is very, very low. If you want to do this with finite differencing, you need at least 20 by 20. You need at least 400 points to even get an answer, which won't even come close to the level of accuracy that you get here. Okay, this integrals will take a little bit because now we're doing a bunch of them, 1,600 of them to be exact. And the solution, as you can see, there it is. Now it's capturing even the discontinuity of the flux. That peak is capturing right on the nose. This one is still off, but that can be better if I increase the resolution. All right, the last step of this code is, well, what we did, the post-processing. I want to calculate temperatures and gradients anywhere in the interior, okay? So this is what I just wrote on the notes. There's the derivative of g with respect to xi, the derivative of g with respect to yi, the derivative of h with respect to xi. This will be the derivative of h with respect to xi, and the derivative of h with respect to yi. These two. Because remember, I have h broken up in 2 parts. So, basically, let's say I'm gonna pick a point. I'm gonna pick 0.35, 0.45, something that's not in the center. You can pick whatever point you want, all right? So what I'm gonna do is I'm gonna carry out n of these integrals over all the n boundary elements, locating the source point at this location. Okay, this is no longer a matrix, this is a vector. That's why I call it JV, or GV, I'm sorry. It's a vector of G's, of integrals of G. And then I do the same for H. And then I do the same for dg with respect to xi. I do the same for dg with respect to yi. I do the same for dh with respect to xi. And the same for dh with respect to yi. And I perform the summation, same thing we had on the notes. I want to know what the temperature is at that location, and it's a summation of g's times q's and h times t. But now notice that we know all the t's and all the q's on the boundary. And this is the exact solution, 32.361, and that's the BEM solution, 32.358. All right, with only 164 degrees of freedom, I'm able to attain that. And the gradients, which are even more difficult to attain correctly, look how close they are. And the x direction, the derivative of t with respect to x at that location is 30.462. That's the exact solution, and that is the BEM solution, 30.433. And the other one is negative, the flux goes, or the gradient goes negative in the y direction, 31.849 to 31.847. It's very, very accurate. And I can go to whatever level of discretization I want, and those number keeps getting better and better. The round off doesn't accumulate because I'm integrating over a set number of elements. Okay, it just gets slower and slower because those matrices. Keep in mind that this system of equations now, the system of equations I'm solving here, L solve, is 164 by 164. It's not huge, but it does take a little time to especially generating the coefficient matrix G and H. Let's see what happens when I go to one last attempt here. When I go to 101 by 101. Again, this is only 400 points. Okay? There's no internal discretization. It's going to take a while because I have to perform 100 by 100, 10,000 of those integrals, 10,000 of these integrals to fill in the 100 by 100 matrix. I'm sorry, 400 by 400, that's more than 10,000. We have 400 elements by 400, that's 16,000. And the solutions took a little while. Well, that's indistinguishable now. The fluxes and the internal solutions, let's see. Well, they're in the second or third decimal place, the error. Okay. And as I said, there's, at least when solving diffusion problems like this, there's nothing that comes even remotely close to the level of accuracy that you can get with these. It is more mathematically rigorous. There's a lot of under the hood stuff that you need to do, but the answer is the right answer. Okay, any questions? So I'm gonna post this spreadsheet on Canvas for you to play with. More than likely, you're not gonna have to use it for the project. I'm gonna write an actual code that you will have to implement for certain types of problems to work on project number 2. Any questions again? All right, so I'll see you Tuesday.